In this video, we're going to examine whether the capital asset pricing model, or CAPM, holds in reality. Now, this is important not just for investment managers, but for people working in corporate finance as well. Why? Well, when you work in a company and you're assessing a project and wanting to understand whether you should invest in the project or not, you think about the cash flows that the project generates, and then you discount those cash flows back to the present day using some cost of capital or discount rate. Typically, managers use the CAPM to calculate their discount rates. If the CAPM doesn't hold, then calculating discount rates using the CAPM is not going to be very useful. The CAPM, if you recall, implies that investors are only rewarded for bearing market risk. And market risk is measured by beta, and it's the extent to which a stock moves with the market, holding everything else equal. So far, we've talked about beta as a measure of market risk, but we haven't discussed how you would measure market risk. If the stock market has a return of 1%, what would we expect to happen to the return of Merck? We can actually answer this question using something called regression analysis. And regression analysis examines the relation between a dependent variable and an independent variable, or independent variables. You've probably heard of regression analysis, and you may well have actually done this in Excel before. But we'll have a very brief review here. In regression analysis, we're looking at a relationship between two variables, y and x. And what we want to know is, what impact does changing x have on y? So in this example, y is the dependent variable and x is the independent variable, and we want to see how changes in the independent variable affect the dependent variable. If you think about the stock market and estimating betas, we want to see how the returns on the stock market affect the returns on Merck's stock. So to estimate betas, we'd want to have Merck's returns as the dependent variable and the market returns as the independent variable. Now, regression analysis does rely on several key assumptions. The first assumption is that there is a linear relationship between x and y. The second assumption is that the error terms must have a constant variance. The third assumption is that the error terms must be independent. In other words, if the error term was positive yesterday, it shouldn't be positive today and tomorrow and the next day, because that would suggest that the error terms are not independent. Finally, we typically assume that the error terms are normally distributed, and we talked about the normal distribution in the last video. If these assumptions are violated, then your estimates of beta based on a regression may not be quite correct. In practice, when estimating betas for stocks, people typically use the market model and run a simple regression, and they don't worry too much about whether all the assumptions are met perfectly. Here is the regression we would run. We have the returns on Merck in month T, and they are going to be related to the returns on the market in month T. Beta will tell us how much Merck's returns respond to changes in the market returns. Why do we have an error term in this model? Well, the error term is in this model because no stock return will be perfectly explained by the market returns. Recall we talked about systematic or market risk and firm-specific risk. The error term is going to pick up all the firm-specific risk, such as a lawsuit launched against Merck for drug that has unintended side effects. That would be captured by the error term. In this video, we're not going to work through how you do this in Excel. We're just going to go through the ideas and the concepts. In class, we're going to work through how to do this in Excel. Now, how do we test the CAPM? The first test we're going to look at is called a cross-sectional test. Given betas for each firm and given average excess returns for each firm, the CAPM implies that there should be a positive relation between the betas and the average excess returns. Remember that the more market risk we take, the higher the stock returns the higher the returns we should earn. As a reminder, excess returns are just going to be equal to the raw returns minus the risk-free rate, and that's what we're going to term excess returns. For the remainder of the course, we're going to talk about excess returns a lot. So make sure you understand that excess returns are the raw returns minus the risk-free rate. To conduct the cross-sectional test of the CAPM, what we're going to do is run a regression. And what we want to see is there a relationship between average excess returns and beta? If the CAPM holds, we think that the higher the beta, the higher the average excess returns. So we think there's a positive relationship between average excess returns and market risk. Now let's see how we test this. We want to run a regression, and we don't observe expected returns minus the risk-free rate. We can calculate the average excess return, and what we're going to do is run a regression of the average excess return on an intercept, so a constant, which I'll call gamma 0, plus a slope coefficient, I'll call it gamma 1, times by the beta for stock I, plus an error term. This is the regression that we're going to run. What does the CAPM imply about the coefficients for gamma 0 and gamma 1? To see what the CAPM predicts the coefficient should be for gamma 0 and gamma 1, we've got to try and match up these two equations, the CAPM equation and our regression equation. First of all, we can see that the expected excess returns are matched up with our average excess returns, so these two things are approximately the same. We have a beta here, which matches up with the beta I in the CAPM equation. Now, with the beta I in the CAPM equation, it's all multiplied by the expected market risk premium. If we want the regression equation to match the CAPM equation, what should gamma 1 be equal to? Well, gamma 1 must be equal to the expected excess return on the market. What about gamma 0? Do we have an intercept in our CAPM equation here? The answer is no, we don't. There is no intercept. It says, the CAPM says that expected excess returns are going to be equal to the beta of the stock times by the market risk premium. There is no intercept. How do we get rid of the intercept? Gamma 0? Well, gamma 0 must be equal to 0. Then it disappears. It drops out of our regression equation. And we can check this by just plugging in the values for gamma 1 and gamma 0, and you'll see that we get back to the CAPM equation. So the CAPM predicts that if we run a regression of excess returns on beta, that the slope coefficient, or the coefficient on beta, will be positive and equal to the market risk premium, while the intercept, gamma 0, will be equal to 0. How do we test these hypotheses? We have to go through t-testing, and I'm sure that you have covered this in the past, but you've probably tried your best to forget it. So we'll spend a bit of time now going through it. We want to test a hypothesis. Our null hypothesis, H0, is that the coefficient, or a coefficient, is not significantly different from 0. The alternative hypothesis is that the coefficient is significantly different from 0. To test this hypothesis, we have to use a two-tailed t-test. And what we do with the t-test is that we take our estimated parameter from our regression. In this notation, that's the beta hat. We subtract 0, which is easy, and we divide through by the standard error. The standard error represents the uncertainty associated with our estimate of the beta. Statistical packages automatically calculate the standard error for each coefficient in a model, so you don't need to worry about how we calculated the standard error. You just have to calculate the t-statistic. And for large samples, if you've got 60 or more observations, there's a rough benchmark. If the absolute value of the t-statistic is greater than 2, then we would reject the null hypothesis that the coefficient is not significantly different from 0. We would say there is evidence that the coefficient is significantly different from 0 at a 95% confidence level. If we think about our tests of the CAPM, we have two things we need to test. One would be the intercept, gamma 0 is equal to 0. And our second test is that we think that gamma 1 should be what? It should be greater than 0 because it should be equal to the expected market risk premium. To test prediction number 1, we use our standard t-test described here. So we would calculate our estimate of gamma 0 minus 0 divided by the standard error. And we would do a standard t-test there. To test the prediction that gamma 1 should be greater than 0, we're going to ask, is gamma 1 equal to 0 or not? In other words, the null hypothesis will be that gamma 1 is not significantly different from 0. And we will do a t-test for our estimate of gamma 1 minus 0, all divided by the standard error. And what we would hope, if the CAPM holds, is that for hypothesis 1, that gamma 0 equals 0, we would hope that we would be unable to reject the null hypothesis that gamma 0 does equal 0. And for the second hypothesis, that gamma 1 is greater than 0, we would hope that we could reject the null hypothesis that gamma 1 is not significantly different from 0. At first, testing the CAPM and hypothesis testing may seem complicated. That's why I want to expose you to this now, and then once you see it again in class, I think you'll see it becomes easier. Fama and French, in 1992, did conduct this cross-sectional test of the CAPM over the period 1940 to 1990. And they find no evidence of a positive relation between beta and average returns. In fact, they find that investors are not rewarded for taking market risk. In other words, investors could invest in low beta stocks or high beta stocks, and it wouldn't affect the average excess returns that they would have earned. Well, this is not good for the CAPM, strong evidence that the CAPM doesn't work. What's more, Fama and French found that firm size and book-to-market equity ratios could explain average returns. Firm size was negatively related to average returns, while book-to-market equity ratios were positively related to average returns. How did they test this? Well, they ran a regression. And their regression was very similar to the CAPM regression, but it had a slight addition. They looked at average excess returns and said that average excess returns are going to be related to an intercept plus gamma 1 times by the beta for each stock plus gamma 2 times by the size of each stock plus gamma 3 times by the book-to-market ratio for each stock plus an error term. And what they found that gamma 1 is approximately equal to 0, gamma 2 is less than 0, size is negatively related to average excess returns, and gamma 3 was greater than 0. Book-to-market ratios are positively related to average returns. This prompted many people to suggest that the CAPM is dead. There is absolutely no evidence that the more market risk you take, the higher the average returns you earn. While some people rushed to condemn the CAPM and say how bad it was and how it clearly didn't work, others stood back and said, well, you've got to slow down here. There are considerable statistical difficulties when testing the CAPM in the cross-section. To test the CAPM, we have to first estimate betas. Once we've estimated betas, we then have to regress the average excess returns on those betas. The problem here is that we have to use estimated betas, not the real betas. Maybe if we had the real betas, the CAPM would hold. But because we're using estimates of the betas, maybe we've got bad estimates. And because we're using bad estimates of betas, so we find the CAPM doesn't hold. But it's not because the CAPM actually fails in reality, it's because our betas are poor. And Miller and Scholes in 1972 actually highlighted that this is a major problem, and that using estimated betas will lead to a downward bias in the estimated risk premium, gamma 1, and an upward bias in the intercept. In other words, the estimated risk premium would fall towards 0, while the intercept would rise up. This is actually consistent with what Fama and French found. They found there was no relation between betas and average excess returns. But maybe that was due to the use of estimated betas. And this is actually a problem that I have been working on as well. And I've been trying to develop a new statistical approach that controls for the problem of estimating betas. And when you do control for this problem that you have to estimate betas, I find robust evidence that is consistent with the CAPM. Investors are rewarded for bearing market risk, and the estimated market risk premium is anywhere between 7% and 10% per year, which is consistent with the average excess returns that we see for the S&P 500 index over 30, 40, 50 years. In addition, I find that stocks with no market risk earn returns that are equal to the risk-free rate, which is exactly what the CAPM would predict. Recall that expected excess returns on a stock are going to be equal to the expected market risk premium times by the beta. If the beta is 0, the expected excess return should be 0. In other words, the expected return is equal to the risk-free rate. So I find fairly robust evidence that the CAPM does in fact hold. There's a second approach to test the CAPM, And I would call this a time series approach. For each stock I, we're going to run a time series regression. So we're going to gather all the monthly returns for stock I together. We're going to calculate the excess returns in each month for that stock. And we're going to regress the excess returns in each month on an intercept called alpha plus beta times by the excess returns on the market plus an error term, as always. If the CAPM holds for a stock, what should the value of alpha be? This is the second test. What is the value of alpha? To see what it should be according to the CAPM, we again have to match up the terms. We have in the CAPM equation, we have expected excess returns, which we're going to match here with excess returns each month. We also have beta times by the expected market risk premium, and in our regression equation we have beta times by the actual excess returns on the market. So this term matches up here. What value must alpha take on in our regression if the CAPM is going to hold? Alpha must be equal to 0 if the CAPM holds. That's the only way that we can match these two equations. This is a more simple test. We're testing if the intercept of our regression is equal to 0. Once again, it was Fama and French who looked at this time series test of the CAPM. And they looked at 25 portfolios over the period 1963 to 1990. And these portfolios were formed based on firm size and book-to-market ratios. So Fama and French sorted firms by firm size and by their book-to-market ratios, and then allocated them to different portfolios. When they ran the regression for each of their 25 portfolios, what they found was that the alphas were significantly positive for small firms with high book-to-market ratios. And this is not consistent with the CAPM. The CAPM says that alpha should be equal to 0 across all stocks and all portfolios if the CAPM holds. So this again seems to be evidence against the CAPM. But once again, there are statistical concerns with this approach. Fama and French estimated the model using over 30 years of monthly data. But the beta for those portfolios, for a portfolio is likely to change over time. And if you don't allow the beta to change over time, then it leads to an upward bias in the estimated alphas. So it's possible that the results Fama and French found was not due to the CAPM failing, but rather it was due to an upward bias in the estimated alphas, or because of statistical problems. Ang and Chen recently published a paper that shows that when beta is allowed to vary over time, there is much less evidence that alphas are significantly greater than 0. The CAPM is a very elegant theory, but it's very difficult to test. The evidence regarding the CAPM is mixed. Over the last 3 decades, the evidence has mounted against the CAPM. But recent evidence that incorporates more sophisticated statistical techniques suggests that actually the data may be consistent with the CAPM, and that the reason we've been rejecting the CAPM is due to statistical problems, not problems with the theory. The verdict is still out on the CAPM. There will be debate about this for many years to come. The final question to ponder is that if the CAPM doesn't hold, what should it be replaced with? In other words, how should we think about risk and return? The CAPM makes intuitive sense. The more market risk you take, the higher your expected return should be. If that's not true, how do we think about risk and return? At present, there have been very few alternative models proposed, but this is an area of active research. That's all I want to cover in this video. I will see you in class where we will implement these tests of the CAPM in Excel.